So like you might have experienced in the past with fractions, moving on from the basic introduction and the elements of simplifying or reducing fractions, the next nicest thing to handle would be multiplying and dividing. So multiplying. Officially speaking, we want to multiply straight across in our numerators and multiply straight across in our denominators. And as a final part to any problem with fractions, we want to make sure that our answer is reduced as much as possible. So our final step, as you'll see with not just multiplying, but the dividing, the adding, the subtracting, final step is always to consider the possibility of reducing. We can say more simply, we're going to multiply straight across, then reduce. So to prove to you that those same comments apply to numerical fractions as they will now apply to our rational expressions containing polynomials, 2 over 3 times 9 over 11. If I multiply straight across, quite literally, 2 times 9 on top, 3 times 11 on the bottom, when I consider whatever common factors might be appearing in the numerator and denominator, in this case we have a 3 as a factor of 9 on top, 3 is a factor of 3 on the bottom. And so we can slash things out there in order to get a 2 times 3 gives us 6 on the top, and a 1 times 11 gives us 11 for the bottom. Exactly the same sort of comment here for the next example. Multiply straight across. So multiply my numerators together by simply putting each individual numerator inside a set of parentheses. Write one big old fraction bar, multiply straight across in the denominator, and that means just putting parentheses around my denominators. That step is complete. The only other thing to worry about, can I reduce? And in this particular case, fortunately, things are already factored for us, and so we can see clearly that there is no reducing that can take place, so this is in fact our final answer. Moving on to do one together now though, x squared minus 2x minus 8 on top, x squared plus 6x plus 9 on the bottom, clearly not factored already, but better than other kinds of expressions, times the expression x squared plus 2x plus 3 on top, x squared minus 3x minus 4 on the bottom. Our first step, again, is to multiply straight across. So, to show you a little bit of the dirty way of doing things here, we can go ahead and take that original problem, and when we copy things down, the quick and dirty way of doing things would be to extend our fraction bar, like so, and then put each numerator inside a set of parentheses, put each denominator inside a set of parentheses, and there's the first step right there. We have multiplied straight across. That part's done. The time-consuming part of multiplying and dividing problems really comes down to the reducing aspect, because in problems like this, where things are not already factored for us, we've got to go through our factoring checklist, and we've got to factor, and in this particular example, we've got to factor all four of these expressions if possible, and they're at least looking like they have the potential to be factored. So if we start with the x squared minus 2x minus 8 that is at the beginning of our now larger numerator, using our factoring checklist, there is no greatest common factor. There are 3 terms, so we use the AC method, and we come up with a parentheses x minus 4, parentheses x plus 2. Moving on to the other part of our numerator, we have x squared plus 2x plus 3. There is no greatest common factor. There are 3 terms that appear. If we try the AC method though, in this particular case, we find the AC method will not yield any results, and so the x squared plus 2x plus 3 cannot be factored. Down in the denominator, we have our first expression, x squared plus 6x plus 9. There is no greatest common factor. There are 3 terms, so we use the AC method again, and we have x plus 3 times another factor of x plus 3. And then we have the other part of that previous denominator, x squared minus 3x minus 4. Again, no greatest common factor, but 3 terms means that we try the AC method. Here the AC method works and gives us an x minus 4 times an x plus 1. Now with everything completely factored, we look for, again, any common factors that appear in both the numerator and the denominator. So anything that appears in both the top and the bottom, well, we have an x minus 4 in both the top and the bottom. So we can slash those out. As far as now constructing our answer, we could very straightforwardly just copy down the factors that do still appear in the numerator and in the denominator. Like so. Again, this is the very direct way of working through things. But what this brings up is something that we haven't seen in the other examples with rational expressions so far. Is there anything that we can do with the x plus 3 times the x plus 3? Well, we have the comment from working with polynomials that said we can shorten that down by using exponents for any sort of repeated factors. So we do have the option of having our denominator written in a slightly different fashion. For instance, we could have our denominator where the x plus 1 shows up first and the x plus 3 would have a power of 2. I'm choosing to write that x plus 3 with a power of 2 at the end of that denominator so that power of 2 does not somehow get lost in the mix or accidentally overlooked. So we've got these options, the more direct or the slightly more condensed version, that would be options to us for writing our answer. But the basics again are that we're multiplying straight across, and then we are reducing. And so for these multiplication problems, the reducing seems to be a much more time-consuming part, where we would have to go through all of our factoring procedures in order to get things factored as much as possible to see what may or may not be slashed out. Now, if you recall the division of numerical fractions, we have previously said that we would transform division problems into multiplication problems, where we would rewrite by using multiplication by the reciprocal. And we said that we could very simply state that part of the procedure as keep, change, flip. Referring to the first fraction, we keep that. The division would be changed, and the only logical thing to change it into would be multiplication. And the second fraction would be flipped. So this exact little comment, which was very friendly to us, is something that we can use again, even though we're not talking about exactly the same kinds of fractions. Turns out we're talking about the same kind of process, though. So dividing with what amounts to be fractions, keep, change from division into multiplication, flip the second fraction. Then we've got a multiplication problem, so we can say for our second step that we just simply multiply, which we now understand to mean that we're going to multiply straight across, and then we are going to, at the very end, always look for any sort of reducing that might be possible. When we have things that are already factored for us, we can see quickly whether or not there are any common factors on the top and bottom for us to slash out as part of that reducing, which we do not in this first case. We'll see how things turn out in the second case here, where, again, what we are saying, and to color code things in the same sort of fashion as those previous two examples. Keep the first fraction. So we're going to write that in black, and keep meaning that this is going to be exactly the same as it was in the original problem. So the numerator and the denominator are just being recopied here. Change, meaning that we are going to be changing from our division problem to a multiplication problem. And then flip, referring to the second fraction in this example, meaning that we need to take the numerator of that second fraction and flip it down into the denominator. And we need to take the denominator of that second fraction and flip it up into the numerator. Now we have a multiplication problem like the several that we had just discussed. And again, the quick thing to say is that we would be multiplying straight across. So just to show you the quick and dirty version of that, we are talking about taking that and we're going to extend our fraction bar so that it covers up our multiplication symbol. In this particular case, we actually don't need to put in any other parentheses since our numerator is good to go and the other numerator is good to go. We can look at this, despite the gap, as being just all stuff that's multiplied together. Likewise, for the denominator, we can look at that as, again, stuff that's already all being multiplied together, which means we've accomplished that part of our multiplication process. We multiplied straight across. Now, the other part, again, at the very end of any fraction problem, we want to make sure that the final answer we're giving is reduced. So if possible, we want to slash out any common factors that might appear in both the numerator and the denominator. So what we see is that the numerator has an x minus 2, the denominator has an x minus 2. The numerator has an x plus 7, the denominator has an x plus 7. And there does not appear to be any other common factors on both the top and the bottom for us. So we can take our answer from the remaining pieces, and the direct way would be to have the x plus 3 times x minus 1 up on top, and the x plus 1 times x plus 1 on the bottom. Or like we had done a minute ago, we can say that the denominator here could be condensed slightly, where we could write in x plus 1 parentheses squared as a slightly condensed version of that particular answer. Same sort of idea going on here in this final example, though this one is less friendly to us because this one does not already have a bunch of factored numerators and denominators showing up, which means more work for us when we eventually get to that point. We begin again like any other dividing problem, where we're going to rewrite this as multiplication by the reciprocal, aka keep, change, flip. Keep the first fraction the same. So just recopying that as it originally appeared. We're going to change the change the division to multiplication, and then we're going to flip the second fraction. So, now we have a multiplication problem to work out. According to our multiplication process, we would multiply straight across, which again we could do the dirty way of taking that original step here, and though I'm writing a new step for it, I understand the inclination to do things in a slightly lazier fashion. We can extend our fraction bar, and we can put parentheses around our numerators and denominators. So now officially, with the way that this is written, it is correctly multiplied straight across on the top and multiplied correctly straight across on the bottom, though there's no extra work going on. Now, we've done the multiplying, but again, the final issue is always to make sure that our answer is as reduced as possible, and that's not something that we can tell quickly from the way that things are currently written. What we're going to have to do is run through our factoring checklist and see if there is in fact anything common, a factor that is common to both the top and the bottom. So the first expression in the numerator has a greatest common factor of 3x. When we factor that out, we would still have a parentheses x squared minus x minus 12. And then looking at that x squared minus x minus 12, it has 3 terms. We can use our AC method, and we would have, coming out of the AC method, x minus 4 times x plus 3. Now don't forget that you do have another x minus 4 that was the second numerator. So there's another factor of x minus 4 that we have just now seen come into play. But now our numerator is fully factored, and we can go back and check out how things are going with our denominators. Well, if we look at our denominators, we do not see any greatest common factor. So for the moment, I will simply recopy those 2 expressions in the denominator. And then here, in my next step, I will consider the next part of my factoring checklist, which is how many terms do we have? Each of those denominator expressions have 3 terms, so yet again, 2 more occasions of working through our AC method to come up with the factors. The x squared plus 7x plus 10 would be factored as an x plus 5 times an x plus 2. The x squared plus 6x plus 5 would be factored as an x plus 5 times an x plus 1. Now with everything fully factored, finally, is there anything in common? No. We just don't know how things are going to turn out. We don't know whether we'll be able to reduce or not, unless we actually go through all of the trials and tribulations of factoring those numerator and denominator expressions. So sadly, all of that work has not resulted in any sort of shorter answer. It has only simply created the confidence that we're good to go. The answer that we originally came up with here is an acceptable version. The answer that we have here is also an acceptable version. By noticing that we have some repeated factors in the numerator and in the denominator, we could also choose to have one other type of answer where again we would condense things, and the rationale here is the factors that end up having exponents on them, I'm going to write at the end of the numerator and also at the end of the denominator so that I am less likely to overlook those powers. It's less likely that the power would get lost in the middle as I am reading through those numerator and denominators. So this would be a third version, an acceptable version of the answer. The first one, since there turned out to be no reducing that could take place, this would be an acceptable version. The factored version that we had where we did not bother to do any sort of condensing work, or the factored version that does have some slight condensing, would be any of those three acceptable answers for us. But again, we can't know whether reducing will take place unless we go through the trouble of factoring as much as possible everything that we have in the numerator and everything that we have in the denominator. So sometimes that work favors us by creating a shorter answer because reducing does take place, and sometimes it does not. So be it.